An analyst suspects that in the most recent year, excess returns on stocks have fallen below 5%. Wants to study whether the excess returns are less than 5%, designating the population mean as mu, which hypotheses are most appropriate for her analysis. So there is our mu. We're suggesting 5%. And we have some possible distribution around which statistically in between some deviation here, we would say, well, it's no different than 5%. This would be if we were testing whether it was less than 5% or more than 5%. That is a two-tailed test. And we're only testing whether they've fallen below 5%, so we can get rid of alternative A right away. So let's just change our distribution here. This is what we're concerned with, that statistically, if we're far enough this way, below 5%, we are below 5%, which makes it a left-tail test. So the alternative must point in that direction. There it is right there. Your answer is B. The book says, or the reading says, no, it is C. But this is pointing to the right. And that is the incorrect area that we're testing, just so that you have an idea. If we're calculating a z-value equals some observed value minus the mean, and since we're using a population, we can just use a variance. If it were below 5% and it were significant, we would expect x would have to be below mu. So let's take 1, for example, minus our 5. Just something far enough below over our variance. We know our variance must be greater than 0, which means we would have a negative z-value. Negative z-value. This would give us a positive z-value. So it cannot be C. Which of the following statements about hypotheses testing is correct? The null hypothesis is the condition a researcher hopes to support. Actually, the null is the condition the researcher hopes to reject. And as I said in the video, that is not always true when you get to regression. And at level 2, multiple regression, there are some tests where we do not want to reject the null. But generally, the null is stated as a condition that we must first reject in order to accept something we are, or at least we hypothesize is going on. The alternative hypothesis is the proposition considered true without conclusive evidence to the contrary. The null is the proposition considered true. So the null is considered true unless we can reject the null. And the alternative hypothesis exhausts all potential parameter values not accounted for by the null. Yes. If the null is equal, the alternative is not equal. If the null is less than or equal, the alternative is greater than. And if the null is greater than or equal, the alternative is less than. So C is correct. Which of the following statements is correct with respect to the null hypotheses? It can be stated as not equal to. We can stop right there. The null is always tested at equality. It cannot be stated as not equal to. It says provided that the alternative is stated as equal to. No. Let's skip B. We know that it's going to be right. In a two-tailed test, it is rejected when evidence supports equality between the hypothesized value and the population parameter. Well, you don't reject the null if you have equality between the hypothesized value and the population parameter, because that is the null. So we can get rid of that. Along with the alternative hypothesis, it considers all possible values of the population parameter. Yes, that is correct. Which of the following statements regarding a one-tailed hypothesis test is correct? The rejection region increases in size as the level of significance becomes smaller. The rejection region, and we'll work with just a right tail here, and let's say 10%. There's your rejection region. If it's 5%, that would be your critical value. Notice what happens to the rejection region. It gets smaller. It doesn't increase. Get rid of that. A one-tailed test more strongly reflects the beliefs of the researcher than a two-tailed test. Yes, it does. So let me put it out in words. Let's say we're testing for equality versus no equality. What we're saying is, look, I don't know what the real value is, but I know it's not that. Whereas if we're testing a one-tailed, we're saying it's not that value, it's going to be something greater. I have an opinion of where it is. It's going to be greater or it's going to be less, as opposed to saying, look, I don't know what it is, I just know it's not that. So yeah, it's a stronger statement than saying, it could be higher or lower, I don't know, but I know it's not that. The absolute value of the rejection point is larger than that of a two-tailed test at the same level of significance. it would be smaller. So let's draw that out and make sure we see it. There's a one-tail test, and let's say that this is 5%. And now let's do a two-tail test. Well, two-tail test would look like this, because now you have to split the 5% among two tails. So there's 5%. So this will be a larger critical value than a one-tail test. So the one-tail test, the absolute value of this would be smaller. And we say absolute value because it could be this way, right? And this is the absolute value here. So the absolute value of this would be smaller than the absolute value of a two-tail test. This is saying the absolute value of the rejection point is larger. It would be smaller. So we can get rid of that. If a researcher selects a 5% level of significance, and we know level of significance is alpha, for a hypothesis test, the confidence level is, and our confidence level is 1 minus alpha. So 1 minus 5% is 95%. A hypothesis test for a normally distributed population at a 5% or 0.05 significance level implies 95% probability of rejecting a true null hypothesis. No, it would be a 5%. We can get rid of that one. 95% probability of a type 1 error for a two-tail test. Again, that's only 5%. Actually, I'm putting check marks when I should be putting X's. 5% critical value rejection region in a tail of the distribution for a one-tail test. That's exactly what it means. The value of a test statistic is best described as the basis for deciding whether to reject the null, accept the null, or reject the alternative. We either reject the null or fail to reject the null. We do not accept the null. The null is a statement that is assumed to be true, so we don't have to accept it. Its existence is already there before we test. We have to get rid of it. So we either fail to reject it or we reject it. So we can't accept. We can get rid of that. And we never reject an alternative. We just reject a null in favor of an alternative. So the only thing we can do is reject the null hypotheses. Okay, which of the following is a type 1 error? And the next one, a type 2 error, is best described as. I find it easy just to replicate that little 2x2 matrix in the reading to keep this straight, because I'll tell you, sometimes I get confused with the word rejecting a false, accepting a true. I get confused with it. So I just DNR and R for do not reject, and TH naught and FH naught. And I know that these two are correct. And here's my type 1, here's my type 2. And from there, it's pretty straightforward. The following is a type 1 error. Well, what's a type 1 error? Rejecting a true null. There it is, rejecting a true null. Rejecting a false null, rejecting a false null. Right away, we see that as a correct thing to do. And failing to reject a false null, which means we do not reject a false null, we see that as a type 2 error. A type 2 error is best described as, here's type 2, not rejecting a false null, rejecting a true null. So rejecting a true null, that's a type 1 error. Failing to reject a false null, do not reject a false null. There we go, option B. And failing to reject a false alternative, well, we don't worry about the alternative, so we're good on that one. The level of significance of a hypothesis test is best used to calculate the test statistic. You don't even need the level of significance to calculate a test statistic. We can get rid of that. Define the test's rejection points. Yes. Specify the probability of a type 2 error. It does not do that. It specifies the probability of a type 1 error. Remember, this is alpha. This is 1 minus alpha. This was beta. This is 1 minus beta. 1 minus beta, also called the power of the test. I know that's terrible writing, but you get what I'm doing there. Define the test's rejection points. The probability of correctly rejecting the null is the, let's do our little thing, DNR, R, TH naught, FH naught, correct, 1, 2. And this is the power of the test over here. The probability of correctly rejecting the null, so we're rejecting, and if we're rejecting, we need to be correct. We must be rejecting a false null. Here we are, is the power of the test. Is power of a test. P-value is the lowest alpha to reject H naught. It is not the probability of correctly rejecting the null, so we can get rid of that. And the level of significance is alpha, which is the probability of making a type 1 error, so we can get rid of that. B. The power of a hypothesis test is, and let's do our Little chart again, DNR, R, T, H naught, F, H naught. This is correct, this is correct, this is type 1, this is type 2. This is alpha, this is beta, this is 1 minus beta, which is the power of the test, and this is 1 minus alpha, which is our level of confidence. The power of a hypothesis test is over here. Equivalent to the level of significance? No. The probability of not making a type 2 error? Well, if this is the probability of a type 2 error, 1 minus beta is the probability of not making a type 2 error. Yes. Unchanged by increasing a small sample size. No, it would be changed. The power of the test would be changed by increasing the sample size. So we can get rid of that. In the step, stating a decision rule in testing hypotheses, which of the following elements must be specified? Critical value, power of a test, or value of a test statistic. In going through the steps for hypotheses testing, we don't calculate the power of a test. The power of a test is correctly rejecting the null. We don't actually calculate it. We specify a level of significance, but we don't calculate or specify power of a test, so we can get rid of that. Critical value or test statistic. So step 4 is to state the decision rule. Step 5 is collect data and calculate the test statistic. Well, here's the value of the test statistic. That is step 5. We can get rid of that. We would specify the critical value in the decision rule. Reject H naught if test statistic is greater or less than this critical value. Which of the following statements is correct? Oh, by the way, if you're in the reading itself has B. I'm not sure if CFAI has corrected it by now. The reading has B, but the explanation of the answer is for A. However, it says B is correct and then begins to explain why A is correct, so just ignore that. A pooled estimator is used when testing a hypothesis concerning the. And what are we doing when we pool? Well, what are we pooling, first of all? We're pooling variance. If we have two samples that we feel are independent, and we're testing the differences between the means of those samples, we can pool the variance. But it's a test of the differences between means. So it's testing hypotheses concerning the equality of the variances. Nope, we're pooling the variances. We're not testing the variances. Difference between the means of two at least approximately normally distributed populations with unknown but assumed equal variances. Yes, we assume they're equal variances, is why we can pool them. Differences between the means of two at least approximately normally distributed populations with unknown and assumed unequal variances. No, we did not look at the case of unequal variance. There is a case of differences between means with unequal variances. We just didn't look at it. When evaluating mean differences, this is not a difference of means, this is mean differences now. That's the D statistic, right? We calculate a D statistic for the difference. When evaluating mean differences between two dependent samples, the most appropriate test is, since it's still means, we can get rid of chi-square test right away because that's a test of variance. A z-test is a test of a single mean. We can get rid of that. It is a paired comparison test. A chi-square test is most appropriate for tests concerning, and we're looking for variance here, right? A single variance. Yes, a chi-square test is a test of a single variance. An f-test is a test of two variances. Differences between two population means, we can get rid of as soon as we see means. In fact, we could have answered this one even if we didn't know it was single variance. The other two had means in them. Which of the following should be used to test the difference between the variances of two normally distributed populations? Since we have two variances, it's not going to be a chi-square, which we don't have here. We're testing variances. We can get rid of t-test. We can get rid of paired comparison test because they don't test variance. We have an f-test. A non-parametric test is most appropriate when the A, data consists of ranked values. Yes, that is appropriate for non-parametric. The validity of the test depends on many assumptions. No, and when the data do not meet any assumptions, non-parametric test is appropriate. If it depends on meeting many assumptions, you're looking at parametric testing. We can get rid of that. Sample sizes are large but are drawn from a population that may be non-normal. No, population sizes are small, n less than 30, and is drawn from a population that is non-normal. We must go with A. In which of the following situations would a non-parametric test of a hypothesis most likely be used? The sample data are ranked according to magnitude. Yes, if we have ranks, definitely. The sample data come from normally distributed population. Well, then we could rely more on parametric testing, so we can get rid of that. We're looking for where we would use non-parametric. The test validity depends on many assumptions about the nature of the population. For non-parametric, no, it does not. For parametric, it depends on assumptions about the population, the population distribution, but not for non-parametric. We can get rid of that. 40. An analyst is examining the monthly returns for 2 funds over 1 year. Both funds' returns are non-normally distributed. To test whether the mean return of one fund is greater than the mean return of the other fund, the analyst can use, well, what have we got? We got n less than 30 right away, and we have non-normal. So parametric testing is out. We have to use non-parametric tests. A parametric test only? Nope. A non-parametric test only? Yes. Both parametric and non-parametric? No, because this eliminates parametric testing. We have to use B.